also the importance of the fine tuning and how you can fine tune the LLM models to perform them according to your needs, as well as we will be overviewing the transformer architecture and its applications in the LLMs, as well as some advantages of the low rank adaptation. So we have Aashi Dutt with us, who is the Google developer expert in the machine learning, and she also has 2 years of experience in AI as an AI engineer. So over to you, Ashi.
Thank you so much. Hi everyone. I saw someone raised hand. Do you have a question when starting? Uh, if you have any questions or doubts, just put them in the chat box, and we'll take them at the end. If right? Okay. Thank you so much all for joining in today. And let me just start by sharing my screen real quick. Just let me know if you can see my screen. Okay, so you don't really require any, there are no pre-requirements for this event. Uh, though if you have read about the paper that is LoRA, low rank adaptation, for large language models, it is good. If you have not, I'll take you through it. Then there are some requirements for transformers, understanding transformers, LLMs, if you know about them. But if you don't worry, I will take you through them, and I have planned in a way such that you understand each and every concept before we reach to the actual topic of LoRa and how fine tuning is done using LoRa. So don't worry if you don't know anything about this at all. Okay. So let me just go ahead and present my screen. Yeah. So here we are. Okay. Once again, hello everyone. My name is Ashi, and I am a GD for machine learning and subcategory for Gen AI. And apart from that, I co-founded a health tech startup back in 2020, and currently I'm a master's student at Georgia Institute of Technology, Atlanta. So today we'll be learning about low rank adaptations of LLMs and how you fine tune large language models. And as through the word itself, you understand that large language models illustrate that they are very large in size of parameters, in size of data sets that are required to be trained on, right? So here is a very easy definition to follow along for large language models is that large language models are powerful AI models that are trained on massive data sets of text, not really text, but a lot of around text to understand and generate human like language, human like responses. So we are in this kind of era where we want such models that can mimic the human levels of competence, human levels of contextual knowledge and everything. Like we want our models to behave like humans basically. So large language models are such powerful AI models. You might have used such models by yourself or might have heard about them. So here are a few examples. Maybe BERT models. These were very famous in past. Very basic on when transformers were introduced and BERT was introduced. Very famous model. Then GPT model, if you actively use chat GPT for your assignments, for your work, writing codes or something, GPT models by OpenAI. Then Llama models by Meta, Gemini and Gemma models by Google, Lambda models, Mistral models, and Phi models, right? These are then few examples of such models. But here are few. Let me just go back. I think somebody has some questions here. Slides are not changing. Is this a problem with everyone? Just give me a raise of hand or thumbs up if it's okay. Let me just go ahead and try something else. Let me just wait. Let me just stop sharing and I'll share my screen again. Okay?
I should try like sharing one tab only.
Yeah, I'm trying that now. Okay, right. Does it work now?
Yes, it does.
Cool. So, few of the applications of large language models include text generation. Of course, we have used chat gpts and Gemini, previously known as bard, for text generation, summarizing and doing things. Then chatbots, if you see many bank applications or some nowadays these apps like clothing websites or something, they use conversational ai tools. And then there are text summarizations. Maybe I don't want to read a whole paper of LoRa, I just pass it to some of these large language models and ask it for summary. And then there is natural language processing research. A lot of research is going around LLMs and natural language processing tools that can help researchers to, get to the perfect level of human level interactions, and language learning tools, and finally knowledge exploration. These are just few examples and applications where these LLMs are used. But we don't really want to understand the applications first. We want to understand how these LLMs we can use at our level with our data sets by fine tuning them. So, for that, we have to understand transformers first, right? Every basic concept, every LLM has the same basis, same backbone, that is a transformer. So transformers were introduced back in 2017 by Google, and these were the best of the best models back then, and now are as well, because most of LLMs are based on transformers. So transformers have something different. Like, unlike previous models, these are not dependent on recurrent neural networks or the previous memory. They are based on attention mechanisms. How they work, we'll understand in the next couple of slides. But what a self attention mechanism is that it's a very innovative mechanism through which the model gives weight or importance to different words in different times in a given sentence so that it can predict the next word. For example, say I want to say Ashi went to market. So the next word might be today, might be yesterday, might be some other thing, right? So the next word prediction is dependent on the words that came before in the sentence, right? So these all things are taken in by the transformer, and through its attention mechanism, it understands it so that it can give you the next word prediction, right? Here is the architecture for transformer. I hope every one of you have seen this transformer architecture. If not, we'll understand it very briefly, right? Because we have a lot to cover. So here is it. The small portion that you see is the encoder block, and the large portion that you see, the number of where the number of layers are very large, is the decoder part, right? So what happens initially is we have, say, a number of sentences, and we pass, these are our inputs, right? We give it to the input embedding. So input embedding layer takes the sentences and it converts it into sequence of tokens, like small words, single words. These are called tokens, right? Then these tokens are embedded together to form a sequence of tokens that have some semantic values and semantic meanings. Once that is done, then you move to the next part, that is positional encoding. So now I told you already that we have a sentence and I want to predict the next word. The next word is dependent upon the position of each word in the sentence before it, right? So how do my model knows what was the original position of the words in the sentence, right? I don't know because I don't have a memory like RNNs or LSTMs. I am dependent on self attention. So for that, we do positional encoding. So positional encoding mechanism works in certain way. that when you give it the tokens, it incorporates it into a context vector by incorporating information about the distances between the tokens in the sequence. So one token might be at the starting of the sentence, one might be just at the last or the second last where I have to predict the next word. So what is the distance between those two tokens? That whole contextual information is carried by positional encoder, right? Then the input embeddings are done and positional encoding is also done. You combine it together and then the main part, the main fun starts, right? So that is multi-head attention layer. This is the main core of transformer that differentiates it with LSTMs, with RNNs, and rest of the other models. So what this multi-head attention layer does is when you have that tokens and positional encodings together, now the multi-head attention divides it into three vectors. So if you can see on the left hand side, there is three words written. That is V, K, and Q. So V here stands for value vector, K stands for the key vector, and Q stands for the query vector. These all vectors are the vectors that are being formed from the original embeddings, the input embeddings that we got initially, right? Now, these will be used to calculate the attention score. This attention score will be used next time when we are predicting words, right? So, what happens is that all these three vectors are passed into linear layers. So, there are number of linear layers. Okay, I told you initially we are not passing just a sentence; we are passing number of sentences. The whole work is being done in a parallel combination, right? Then we need a scaled dot product attention. This is the main attention mechanism and it's very basic. So you take in the query and the key vector, do the matrix multiplication, get the score, do some masking if it's optional if you want to do or not, then pass it through a softmax. Then we have a value vector. We take that along, do the matrix multiplication of whatever we got from the combination of the query and the key, and we get the output. This output is then given to the concatenation stage where you concatenate what all outputs, what all attention scores you got throughout in a for number of sentences, and then you concatenate those all together and you put past them through a linear layer. So what's happening here is imagine a high dimensional space and passing it through a linear layer that is flattening it, right? Imagine a 3D space. Now imagine a single space, a linear space, right? So that is what the linear layer does here. Once that is done, next we move forward to the feed forward layer. Feed forward layer does nothing, just multiplies the weights and then passes it to the next level. So that is basically the output of your encoder section, right? So encoder section understood all things about the sentences, the basic tokens, what is the relationship between the tokens. Now it's up to the decoder layer where we actually get the next word prediction, right? So what it does, it uses the output, what kind of output we want, but it is shifted. We are not actually giving the last word that we require. We are just giving it the required context for that. So same thing happens with uh, output and embedding as with the input embedding. But something different happens here is that here we used a masked multi-head attention layer. So what masked multi-attention layer means is that it includes a mask like zeros or ones mask for tokens such that that will appear later in the sequence. So what's happening here is basically our encoder knows everything about the sentence, but we don't want our decoder to know the last word that we wanted to predict, right? So we want to mask or to hide that last word that we want the decoder to predict. So basically where we use a mask, right? Then the output goes into multi-head attention. That is, we have two multi-head attention layers in the decoder part. So because one output comes from the output section and one comes from the encoder section. So from the encoder section, we get the inputs. And what we do is for the second attention layer, we take in it as encoder decoder attention where the target token looks at the source tokens rather than each other, right? Once that is done, again the feed forward layer, again the linear layer does the same work, and it matches to the number of tokens in the output data. And through then, we have a softmax layer where we get the predictability or the probability or logic, what's called, to get the probabilities. Okay, this word has the maximum probability, so this might be the next word in the sentence. That is how the decoder works. It's very basic but very interesting. So I hope you have a very basic gist about how transformers work, right? Next is, once you know about transformers, you want to know about pre-training and fine-tuning. So these are the two words that are used very often, but are kind of used interchangeably sometimes, but they should not be, right? Pre-training basically means that you have a bulk of data. Consider the whole internet, right? Consider the websites, consider GitHub, codes from GitHub, this and there, everywhere. And you have trained your model on that data set. That is pre-training. A large amount of massive data set, maybe in billions, and you have trained your model or LLM on that data set, right? That is pre-training. Then it is fine tuning. Fine tuning is that you have a very limited data set, but you want to make sure that your model is perfect only on a very specific task, but it does not, forget about certain things that it learned from the original data. So think about it like this example. When we were growing up in school, we were taught everything, right? From English, Hindi, math, science, everything, right? But when we grow up as adults, we have to choose a certain field, a certain niche, right? That is fine tuning. Pre training was that you were taught everything. But now, when you are in a certain, say, a niche or a certain profession, you don't really want to go back and understand all those languages or maths and things and stuff, English, this and that you learned at that time, right? No history, no civics, no economics, nothing, because you're in a certain niche. That is fine tuning. You have been fine tuned on certain data, but that does not mean that you forgot about everything that you were taught back in school, right? You have that information in your knowledge base, but now you have a niche that you are trained on a very specific data set and you do a desired task, right? So here is a very brief comparison between pre-training and fine-tuning. And very interesting thing is the techniques and examples. So basically, the examples are pre-trained BERT models on a very large corpus, say a Wikipedia or number of books in your library. Or fine-tuning is fine-tuned BERT model on sentiment analysis. So if I want to, do a sentiment analysis on Twitter data set for saying that something is funny or something is not funny, I would consider the whole data set, different data set. I would consider such examples that would actually, showcase that, okay, this is funny, this is not funny. I won't consider all the information available on Twitter, right? So that is the difference between pre-training and fine-tuning. Here you can see how this works. First is the transformer architecture, the basic transformer architecture, that is the backbone of LLM. Then you train it, that is the pre-training stage. You pass it all the data available. See, here they have archive data, here they have data from GitHub, Wikipedia, that is all unlabeled data. So you're just passing it and you're training the model, that is pre-training. So you got a model like Llama that is passed by Meta. But after that, you pass in a supervised way, a labeled data. So when you pass in the labeled data, you are fine tuning it into certain desired tasks, right? So a pre-trained model, when given a labeled data, becomes a fine-tuned model, that is this model, say alpaca model, right? But there are certain challenges to fine-tuning as well, because fine tuning can be computationally costly, because as I already told you, these models are trained on billions of billions data. So if the data is so big, the model is of course going to be that big because you need such parameters to understand all that kind of data, right? So the computational cost is of course high. The data requirements is of course a big task. Then catastrophic forgetting. There may be causes where your model forgets about what thing it has in its knowledge base when you're fine tuning it. It happens sometimes. Then overfitting. LLMs might be prone to overfitting in case you're fine tuning them because of poor generalization or so, right? So these are few challenges, and now we'll understand how LoRa does it, how LoRa overcomes these challenges. So why LoRa? I've already told you this problem, but consider it again. So say an LLM with 175 billion parameters. Consider the depth of these parameters. It's exciting, but it's daunting to fine tune on a GPU. You have like a limited GPU T4 or something, and what you want to do is fine tune such big model that has 175 billion parameters. So it's gonna be expensive on compute level, right? It requires a vast amount of data as well. So how do you do it? LoRa offers you an alternative way such that you freeze the pre-trained model weights and inject low-rank matrices into each layer. So what is this? We are not putting some injections into the model or something, but how do we do it? We're gonna understand it. So the core idea of LoRa is low rank decomposition, injection into layers, and freezing the pre trained weights. Right? We understand it one by one. First is low rank decomposition and how it is the heart of LoRa. So, what is basically low rank decomposition? The core idea is that you have a large weight matrix of a large model, and you have to somehow decompose it or shrink it into smaller matrices, smaller two matrices. One is matrix A, that is your update matrix, and one is matrix B, that is your rank decomposition matrix. So what does this do is, if your original weight matrix, that is W, your original model, has a weight matrix of shape D cross K, then your A matrix should have a shape of R cross K, and your B matrix should have a shape of B cross R. So what does that mean? And R is the rank hyperparameter here. I'll show you the figure and you'll understand it much better. But what we're going to do is the product of both these matrices A and B is an approximation of change in the original weight matrix. So what we are doing here is we are freezing the original weight matrix that was originally part of the large model, and we are kind of mimicking the same characteristics of that weight matrix, but in a shrunken way, right? We're approximating the change. We're not completely showing that okay, this whole weight matrix is changing this much. We're approximating the change in that original weight matrix during fine tuning, right? And this approximation assumes that change in weight during fine tuning have low intrinsic rank. And why is it important? We'll tell you soon. So here is it. Consider you have an input that is X and it has D dimensions, right? So this is your original pre-trained weights, that is capital W, and it has D cross D dimensions. So instead of using this, what we do is that we have two other matrices, A and B, that are much smaller in size than the original weight matrix, and we use both of them to mimic the characteristics of this original weight matrix, but we also keep it along with us. We are not discarding that, we are keeping it. We are just making sure that any changes that are happening in W during fine tuning are mimicked by A and B, not in W, right? Because W has lots of billions of parameters, we are not gonna work around W, right? And we compile them into H. So now H has much less dimension as compared to anything else. Why low rank decomposition works? So first is rank. I hope everyone knows the rank, or how to find the rank of a matrix. Okay, so it roughly indicates the unique information that is carried in a matrix. Then there is a hypothesis that is the change in weight during fine tuning is primarily low rank. So we want to keep it low because we want to have less number of parameters to fine tune or to update, right? And the efficiency, by decomposing delta W into A and B, we drastically reduce the number of trainable parameters. Then what is injection? So we talked about injection and how injection is actually done. What injection actually means? Injection into transformer layers. Because as I told you initially, that there is a transformer layer that acts as a backbone for this whole LLM model, right? So how does this layer actually works? What injection into transformer layer actually means? In transformer models, the weight matrices of there are weight matrices of attention and feed forward layers, right? Both of these layers have weight matrices, right? And these are very very large, given we have large models with large number of data sets, right? So what LoRa does, it decomposes these large weight matrices into two smaller ones that are low rank matrices, that are A and B. So what we do, we have a target layers, that is our attention layer, and the feed forward layer that have weight matrices. Then we freeze the original weights, W0, we freeze it because we are not going to use it to update it because it's computationally expensive. Then adding a low rank matrix, so adding a low rank matrix, that is our A and B, that decomposes large matrices into the short ones. So a new output for the forward pass, the original model of transformer that I showed you. So our original new output for forward pass would be weight of that layer multiplied by X plus, that is our B matrix into A matrix into X, right? Where X is the input to the layer. So when training, only the matrices A and B are trained during fine tuning, and we are not working around W. So this, what happens is that instead of those billions of parameters in W, we just have to now train those small parameters in A and B. That would take less number of compute, less amount of compute to give us the output. So this dramatically reduces the number of parameters that we need to optimize, right? Next is preserving the pre-trained knowledge. Of course, we want to preserve our pre-trained knowledge. That's why we freeze our base model at the weights of the base model. That is our capital W. And focus adaptation is that LoRa allows you to adapt to specific tasks. So instead of just learning anything, you're focusing on a certain task through a certain data set. So you are not actually you can work around smaller data sets that would be computationally less expensive for you, and you can train your model on new things or new data frequently. Then is the benefits. So the benefits of using LoRa is improved training efficiency, uh, since you have reduced the trainable parameters by around 10,000 x reduction. So LoRa speeds up the training by fewer updates. Then comparable performances. This paper of LoRa showed comparable performances to various tasks that were done by Roberta models, GPT-2 models, GPT-3 models, and finally reduced computational costs that I've already told you. So now the boring part. That is the mathematical formulation of LoRa. That is not really that much boring. It's very easy mathematics and very easy to understand. So we'll go through mathematical formulation, show the equations for low rank decomposition, and how you update the matrices, that how you calculate the updation. Then other training process, how you train LoRa, through gradient descent, and finally inference, how LoRa does not add any new or extra latency during inference because original model weights are not modified. So the kind of inference that you are getting with the pre-trained model, you will have the same latency that with your fine-tuned model. So the performance of the model is not hindered. So here is the mathematical formulation. Mathematically, you have the original weight matrix. I've discussed about that. That is W. Then you have a decompose. You do decomposition using LoRa, and you break it down into A and B. So A here is the update matrix that has dimensions of R cross K, where R is a rank, or rank is also a hyperparameter over here, and it updates the, and it captures the update direction. So in which direction the update is happening. So whether it's forward pass or the backward pass, right? Then rank decomposition matrix, that is B matrix. It has dimensions of D cross R, and it combines the it. This is the matrix that combines the updates, right? And finally, the approximation. So everything here is based upon approximation because we are using both of these matrices A and B to approximate the original weight matrix that is W. So both B and A are comprising together to form delta W. That is, what is the change in W if we fine tune it on some other kind of data on a very specific task, right? So what is the change? That is the basic thing that we want to know. So delta W is basically B matrix multiplied by A matrix, and your new output would look something like this. That is W0, that is the original weight matrix, multiplied by X, that is the input to the layer, plus the change, that is delta W into X. So if you open delta W, you'll get B into A, right? Basic mathematics, nothing more to do over here. So if you do a regular fine tuning or you do a fine tuning with LoRa, what is the difference? See, if you do regular fine tuning, that is, here you have pre-trained weights W, and here you have updated weights, that is delta W, where you have used the original weight matrices and W matrix, and you have used it to create delta W matrix. It is computationally very heavy because it will have the same amount of parameters that W has. But if you do it with LoRa, then it uses those two decomposed matrices that have less number of parameters as compared to W. So delta W is B into A, that is much, much less parameters as compared to the original pre-trained weights. Okay. I hope the difference between fine tuning with LoRa and without LoRa is clear through this illustration. Next is some example of how code works in with LoRa, right? So this is written in PyTorch, but you can write it in any other coding programming language that you like. Uh, so here we have a class of LoRa layer, very basic, and all the mathematics that we've learned previously, we are gonna learn over here. We're just implementing it. So if you have seen the original somewhere here, yeah, this image, just remember this image. Here we have input X, that is our X layer, that has dimension D, right? So our weight matrix was D cross D, right? Now we have A matrix, that was any randomly, random matrix that has size of 0 comma sigma square, that is the standard deviation. But the B matrix is 0. Initially B matrix is 0, right? So if we go next to the coding part again, how do we implement this thing? See, we have standard deviation, so 1 upon torch of square root of a rank. Okay, then our A matrix would be nn dot parameter, so a randomly generated matrix A, that has input dimension, the rank, and multiplied by standard deviation as shown in the figure. Then a B matrix is initially torch dot zeros. It's zero, a matrix of zeros, right? Having the size of rank, comma, output dimensions. And then alpha here is basically a scaling hyperparameter that is applied to the output of low rank adaptation. So what alpha is actually doing here is it's controlling the extent to which adapted layer's output is allowed to influence the original output, right, of the layer being adapted. This can be seen as a way to regulate the impact of low rank adaptation on the layer's output. So if you want like you want more regulation or more impact of LoRa on the output layer, then you can increase the value of alpha. Otherwise, there is no need. So x becomes alpha times of x into a in at b, right? And you return x. Next is training process. We've already talked about it. Let's talk about it again. Initially freeze your base model, that is freeze your original weights. Then initialize A and B, that are our matrices, update matrix and rank decomposition matrix. Then forward pass during both W during training, both W naught, that is your initial weights, into X and B into A into X. Both are calculated to get the output H. During backpropagation, we are not going to mess with that. So during backpropagation, we are just updating A and B, but we are not updating the original weights because we are not going to change them. We have frozen them initially, right? So during forward pass, everything goes right. You are doing the training, but you're not updating those weights because updation happens during the backpropagation, and the gradients are backpropagated, and we are only updating A and B because we want delta W using A and B. We don't want to mess with W, that is the original weights, right? Then you use an optimizer, say Adam or SGD up to updates A and B based on the gradients that you have calculated. And finally, you have the updated matrix, that is W plus delta W, right? You have the change now. Now is the inference. So inference at this is at cost of 0, because as I told you initially that there is no inference cost, because what your model was initially taking time to get you the inference, it will give you the same time to get to the inference after your fine tuning as well. There is no changes to the original model. At inference you can also discard A and B, that is not a problem, because the original model weights, that was original W, has been updated by applying delta W, right? So W is updated with help of delta W. So you don't really have to, keep A and B alongside. You can discard them at inference. And now, because of that, you have efficient computation. So forward pass is actually same as the original pre-trained model. So here is a very interesting thing about LoRa, and how you can save on GPU memory while using LoRa. This will give you a much better understanding of why I was saying W and delta W and everything. Say, let a pre-trained weight matrix W, it has around 1000 cross 1000, it's a 1000 cross 1000 matrix, right? Then weight update matrix delta W during fine tuning would be the same matrix, right? Because original W is same, and you're just mimicking W into delta W. So delta W would have the same number of size as the original matrix. So in this case, delta W has 1000 cross 1000 parameters, right? But if you're using LoRa, what happens is A and B have different sizes, right? We have already talked about it. What's the size of A and B here? Yeah. So size of A is R cross K, right? If W has dimension of D cross K, so in our case, W has dimension of 1000 cross 1000. So K is 1000 and D is 1000. So R cross 1000 is A and 1000 cross R is B, right? Let me go back. So if I take the rank of our model as 2, of the matrix as 2, then A would be 1000 cross 2 matrix and B would be 2 cross 1000 matrix, right? So in this case, the delta W would be 2 cross 2 cross 1000, that is around 4000 parameters. Now you see the difference between the number of parameters with and without LoRa. So without LoRa, it was 1000 cross 1000 parameters, and with LoRa, it is 4000 parameters. So how much difference it has? So with the rank of 2, it has around 250 times fewer parameters. That is how computationally inexpensive LoRa is as compared to normal fine tuning, right? Next is applications of LoRa. So applications of LoRa is basically custom model adaptation. So if you have large models, you can adapt to a specific kind of domain. Then is model compression. So imagine this, you have a large model like GPT model and you want to deploy it on say a smartphone or somewhere. Now, GPT model has like billions of parameters. You cannot fulfill the size and the computational requirement of that model on your smartphone. It's impossible to, have such billion parameters or deploy on your smartphone. Instead, using LoRa, what you can do is you can use these small weight matrices into a decomposed form into low rank matrices, right? And you reduce its size such that it becomes feasible to run on smartphone. And that too without compromising on the performance that we have already seen, right? On fine tuning, we have seen that the performance is not compromised, right? The performance of original model remains the same. Then is the continuous learning. So continually updating your models becomes much easier because how you do that is you just pass in your information, new data that you want to pass, and fine tune a model in that. Because originally all the information is stored in the knowledge base of the model, right? So you don't have to actually pass in all new information. Just pass in the very new information that you want or specific information that you want to pass to your model, and you can update the models with new information without need for full retaining or full retention. Now, very interesting part of how you can use a fine tuning LoRa. It's a very easy project, but you can try and make something of your own like this. I think you might have seen it somewhere before, but if you have not, here is an example of fine tuning and deploying Gemma model on Android. So Gemma model is having around 2 billion parameters, 2 billion parameters with Gemma model, and how we fine tuned it to use it and deploy it on Android, right? So the whole app was around, I think, 2 GB or something, and it was way less compared to what apps you have or any games that you play on your smartphone these days, right? So what we did was we prepared a data set through a science textbook. It's a ninth class science textbook. We took all the chapters, all the information from this, converted that information into a CSV file that had 3 columns. One was the question, answer, and the context. Right? All the information converted into question, answer, and context. Then we used LoRa to fine tune the Gemma model on that given data set. So Gemma model originally is tuned on web documents, on coding, on a lot of textual documents and stuff, but it didn't have a lot of information about the science textbook of class 9. But I wanted some answers specifically for class 9 textbook that was just written or presented in this textbook. So what we did was we converted all the information of this textbook into a CSV file in the form of data set, and we passed it and fine-tuned our Gemma model, Gemma 2 billion model using LoRa, right? So once we did that, then we gave it a prompt saying what is the momentum of an object of mass 5 kgs moving with velocity of 2 meter per second, right? Then we took an inference through fine-tuned model. So you can do that. Just get the inference on your, say, Colab notebook or somewhere, or you can get your information, your output through MediaPipe Gen AI converter and convert it and deploy it on like an Android app that we did, or you can host it on Hugging Face Spaces as well, right? So you can see over here we are asking it a question and it's giving us answer corresponding to the data set that it's trained on, that is the science textbook. Note here that it has not, forgotten all the data set it was earlier trained on. It's just fine tuned on certain data set that we provided it, but it still has that whole thing in the memory set, right? But there are few limitations to these models as well. So LLMs are very much better at tasks that can be framed in clear prompts. So you might have, noticed it yourself that sometimes you pass in one prompt to your, say, chat GPT or Gemini models, and it does not respond back in the right form. But the moment you change your prompt, you get the right answer, right? So LLMs are better at tasks that are framed correctly in clear prompts, but at highly complex tasks that become very challenging for them. Similarly, they struggle with nuances and sarcasm that we humans understand very easily, right? Then LLMs generate responses that are based on the information that they have been trained on, right? The kind of information that I have passed as the developer of that model, right? They don't know what's going on in the real world. They don't have the knowledge bases or a memory to store it, and they may be incorrect factually and maybe outdated as well. So don't really try and apply these things to them and ask fooling questions to these models, because sometimes these models use the data that you provide as training themselves, as fine tuning themselves as well, right? So don't go around and fooling them, and don't ask them futuristic questions that they might not have answers to, because they're not trained on that data. They cannot predict. Then LLMs rely on statistical patterns in language as images, so they don't have that common sensibility as we humans have, right? So these are few limitations that LLMs have, but these are models that are work in progress, and as new models are arriving into the market, they're getting better and better after each time. So in this is about the end of this presentation. Here are a few resources for you. So you can go ahead and now read the LoRa paper. You will understand how the weights are updated in LoRa, using LoRa, how to fine tune your model using LoRa. A bit background on transformer model is very much important. And you can see for yourself a summary blog of LoRa that I wrote myself, and then you can understand LLMs. There is a Google Cloud, very a small um, code lab kind of thing that you can go and try LLMs on. Then if you have access to Vertex AI, you can try LLMs over there as well. Then if you like the project that I demo I recently showed you, you can follow the 3 block series on Medium as well. And once you understand LoRa, then there is one more thing, at least two more things that you can do is try a DORA model. It's basically a different version of LoRa. And second one is try fine tuning with PEF. So PEF is actually a methodology that uses LoRa. So consider PEF as a wrapper around LoRa that helps you to employ it as a specific technique within broader paradigm to fine tune large language models more efficiently, right? So the combination of PEF and LoRa basically reduce the number of parameters that needs to be trained and stored. So it makes the whole process very resource constraining or resource efficient and computationally efficient. So yeah, that's all. Just take a screenshot of the resources, and you can go ahead and try out them yourself. Do read the LoRa paper, and it's very, very much recommended that you understand the transformers paper first. There is one video by Andre Capati by on YouTube around transformers only. You can understand transformers well from there as well. Though it is around like a long video, but yes, it's a very interesting video to understand. So very much recommended that you go ahead and understand transformers before understanding large language models or any of these fine tuning techniques on your own. And yeah, that is kind of all for this session. Thank you so much, and we'll be open to questions. Okay, you want yeah, I'll share these slides in the WhatsApp group. They shared her. So, a beginner in NLP virtual assistant, which can reply queries like ChatGPT, but from for my data in my database. Yes, you can do that. You can do that with RAGs actually. That is much more